of the channel. Today I want to talk about square waves and bandwidth. When I was in the Navy, we studied bandwidth quite a lot in terms of communication channels between different computers, and the word bandwidth means like different things to different people. If you ask somebody at home, what bandwidth does your broadband have, they'll give you an answer in probably megabits per second or something. But if you ask a radar engineer on a Royal Navy ship, he'll tell you it's the difference between the highest and lowest frequencies of a signal. So two different kind of answers, but they're kind of interlinked, and they mean they kind of, what's the word? They're entwined together. So we'll see that here. I want to go over what bandwidth means, how it's linked to data transmission rates or bit rates, and a bit of a mathematical look at it and see if we can get an intuitive idea of what it means. Alright, so first let's look at the Shannon-Hartley theorem. This talks about channel capacities. So the bit rate is equal to the bandwidth times the log of this function here, which is the signal power divided by the noise power, or the signal to noise ratio, right? This should hopefully be a massive number, so we get a nice big gain there, and we can see the bit rate is directly proportional to the bandwidth, right? Bandwidth goes up, bit rate goes up, so it's a very important feature. This video will explore a bit more what that is. There's another guy just down here called Nyquist. Now he determined the number of independent pulses that we can telegraph down a communication channel is limited to twice the bandwidth. So again, if I want to send a lot of pulses, I'm going to need a large bandwidth to do that, because it's limited to less than twice the bandwidth. Okay, so again, it's just another kind of formally stated idea that bit rate is connected to bandwidth. So let's go and look at this graph a minute and think about what bandwidth might mean. So if I take the first Shannon-Hartley theorem, and I've just graphed it in here, I've made the domain x is positive, and the signal to noise ratio is represented by x. So when x is, when the signal noise is twice as big as the noise, x is 2, and I get the bit rate out here of 1.5 or something. But if I increase b, the bandwidth, you can see you get drastic increases in output, right, in the bit rate. So the bandwidth does affect the amount of data we can send. Alright, next I want to look at an actual signal. Now, a man called Fourier, he told us you can make a pure sine wave if you just keep adding infinite harmonics. So what I've got here is a sine wave, fundamental frequency here, and I've added the first harmonic. We're basically adding all the odd harmonics, right? 3 times the frequency, 5 times the frequency, 7 times the frequency. And down here, I've got a third of the amplitude, a fifth of the amplitude, a seventh of the amplitude. Now I could keep adding on these harmonics again and again and again, and I would get closer and closer to a square wave, right? But for the time being, I've just got these fundamental and 3 harmonics. All right. Now, if I was sending this signal to somebody, it's quite slow. I'm limited in how much data I can send by these transition of these pulses. So maybe I could increase it by doubling the frequency. So I double the frequency. Everywhere I see an x, I just double it. 2x, 3x becomes 6x, 5x becomes 10x, etc., etc. I've got 3 harmonics there, and I can see the red signal is doubled in frequency. That means I can send a lot more data, right? It's kind of intuitive. If I send stuff faster, there's faster transitions between ones and zeros, I can get a lot more data down. I've increased my bit rate. But what about the bandwidth then? Well, the bandwidth is the highest frequency, in this case 7 there, minus 1. So the bandwidth of this is 6. What's the bandwidth where I've doubled the frequency? Well, the highest highest frequency is 14 and the lowest one's 2. 14 minus 2 is 12. So the bandwidth is 12. I've doubled the bandwidth, right? The highest frequency to the lowest frequency. I've doubled it, but I can send twice the data. All right, I hope you get a sense of that. Bandwidth, highest frequency minus the lowest frequency. If I double the frequencies, I've doubled the bandwidth for the same number of given harmonics, right? I can increase the bandwidth further and get an even better square wave by simply adding more harmonics. And I want to give you an idea of that here. So when n is 1, I've added one harmonic, and if I just keep adding harmonics automatically with this little summon function I created, you can see it gets closer and closer to a square wave, right? But the closer I get to a square wave, the more bandwidth I need because the more harmonics I'm using, right? And the higher the bandwidth my signal, it's kind of, I want to try and minimize the bandwidth so I can fit more channels in a given transmission medium, right? Every medium like copper or fiber will have an upper limit. It'll have a maximum bandwidth that can cope with. And if I send a large bandwidth signal down there, I can only maybe have 1 or 2 channels. But if I limit my bandwidth of each signal, I can maybe send more channels and more data. I can increase my bit rate. So again, it's an engineering offset. If I want it more like, if I want these transitions from a 0 to a 1 on here, if I want them to happen instantaneously, I need a perfect square wave. To get a perfect square wave, I need infinite harmonics. If I've got infinite harmonics, I've got infinite bandwidth. Can't really have that in the real world. So I need to make a compromise. I need to reduce the number of harmonics. I need to reduce my bandwidth. Then I can send more channels down a signal. I hope that gives you an intuitive sense of what bandwidth is. Now let's look at a practical example. This is some coaxial cable or copper cable, and I can see it's got a bandwidth of 6,000 megahertz. That's great. That means I can send a lot of signals down there, get a good bit rate. But can we do better than that? Well, yes, we can. Recently, we've been using fiber optic, and that can have a bandwidth of up to 1,000 terahertz, right? That's 1 times 10 to the 15. Coaxial is only 6 times 10 to the 9. So it's a magnitude of it's an order of 6 times, order of magnitude larger. It's 1,000,000 times better, right? 1,000,000 times more data. So that's why we use fiber optics, right? They're both not ideal, like they both suffer losses and attenuation in different ways. But sending light with its high frequency allows us to have a large bandwidth. And a large bandwidth allows fiber optics to cope with a lot more data, much higher bit rates. All right. I hope that gives you a sense of what bandwidth means, both from a frequency perspective and a bit rate perspective. They're kind of linked together. It's kind of interesting. I miss doing this at university, you know. We don't get to do this in A-level physics anymore, which is a damn shame. They've taken out the curriculum. Anyway, never mind. That's it from me. I'm going to sign out. Hope you enjoyed that.